Okay, let's go ahead and get started. So we're opening to page 17. And our quick look at the calendar says we have one word topic today, and that word is radians. So today is all about that other kind of way to measure angles that we have mentioned. We've been talking about degrees only, but today we introduced this other thing called radians, just like feet and meters are different ways to measure length, degrees, and radians are ways to measure angles. So we do that today. What's happening on Friday? Project number 5 is due on Friday. Also on Friday, you get project number 6. I want to make sure you have something to entertain yourself with over the break. That said, I actually put project 6 on your table today. So if you have already finished project 5, which I know some of us have, you can get started on it, but officially not assigned until Friday. Any questions on the calendar? Okay, next thing I want to do is take a look at this quiz that I just handed back. I do drop the single lowest quiz grade at the end of the semester. So for some of you guys, I think this will be the lowest quiz grade. But I just wanted to take a look at number 3 because it's really important to me that we're able to do stuff like number 3 moving forward in our trigonometry section. So given a 58-degree angle and a side of 12 on this right triangle, it turns out that we should be able to figure out everything else there is to know about this triangle. You can find the other angle, you can find the other two sides. Finding the other angle is pretty straightforward. I think just about everybody got that right, so we're not going to look at the other angle, but I'm just going to focus on that 58. And all that we knew at this point was SOHCAHTOA. And so suppose that I was interested in finding the length of this side down here. I'll call it x. Looking at the x and the 58, what word would you associate? You have adjacent, you have opposite, and you have hypotenuse. That's opposite. What is the 12 called? Adjacent. So do you guys see that we're focusing our attention on the thing that we want and the thing we know? We want x, we know 12. That's opposite, that's adjacent. That completely governs which trig function we use. Which trig function relates opposite and adjacent? It's tangent, right? It's the TOA part. So what we need to do is use the tangent of that angle. So our equation becomes tangent of the angle, 58, equals opposite. Which one is opposite? X. Divided by adjacent is 12. Are there questions on setting that up? Okay, and tangent of 58 is just a number. It is known. You can look it up on Google. You can look it up on your calculator. You didn't have a calculator for the test, so all you had to do is solve for x by doing what to both sides? Multiply by 12. So x is equal to 12 tangent of 58. And the other thing we were interested in was the hypotenuse. Now, some folks decided that because this was a right triangle and they now knew two sides, what famous theorem could they use to find the third side? Could use Pythagorean theorem, and I gave full credit for using Pythagorean theorem. You know, it's going to be a little bit messy now because it's got a 12 tan 58 in it, but I'd also like us to be able to get it using this trig idea. So I'm going to go ahead and call this side R. And in terms of opposites and adjacents and hypotenuses, what is R? That's the hypotenuse, yes? That's the thing opposite the right angle. So, you know the opposite side is 12 tangent of 58. You know the adjacent side is 12. Which one would you rather use in a calculation? Let's use the 12, right? You're allowed to use the 12 tan 58, but it's messy, and if you've typed it into a calculator, it's got error built into it. So how about we just go back to the 12? So the things we're trying to relate are the adjacent side, still, and the hypotenuse. Which trig function relates adjacent and hypotenuse? It's cosine. So cosine of the same angle, 58, equals adjacent over hypotenuse. Adjacent is 12. Hypotenuse I called R. And now solving this guy for R is actually a little bit tougher than the other equation, but we should still be able to do it. I don't like that R is in the bottom, so what do I do to bring it upstairs? I'll multiply both sides by R. So the R comes over here to the left. R cosine 58 is 12. And then cosine 58 is just some number, so we can divide both sides by cosine 58. So we get 12 divide cosine of 58. All right, so the reason that we spent time looking at this quiz and not the other quizzes is that it's really, really important to me that you guys can take a right triangle and be given an acute angle and a side and find everything else there is to find about that triangle. I'd really, really like us to be able to do that. Any questions on this one? Now, it turned out there are other right answers. So you might have gotten full credit by using not the 58, but this other angle, which we haven't labeled, but that's a 32. And you could use different trig functions, and the answers will look different, and they'll all have 32 degrees in them, and that's fine. So this is not the only answer, but there's no reason to label the other angle, and we could just do everything with 58 if we wanted. Okay, so. All right, so we're on page 17, and like I said, today we mentioned, or we define this new thing called radian. And one other quick announcement, and then we'll start. Again, I'm willing to give a little bit of extra credit to anybody who's willing to stick around and participate in this math competition. It happens today, right after this class in this room. We'll start at like 11:55. You can stay until 12:55, but you can't take longer than an hour on this competition. That's part of the rules. But if you decide you're done at 12:25, then you can leave. So really, you're only committing to half an hour if you decide to participate. But I would ask that you not leave in less than half an hour, because as soon as somebody leaves, nobody else can start after they leave. So it's a half hour up to an hour commitment. Multiple choice tests, you don't need to show your work. Graphing calculators are okay. Like I said, it will kind of push you in new ways. Challenging, but there will be some questions that I think will be accessible to you. So hopefully folks can stay. Okay, so we'll go to number 1, and can we start with Chris B? Okay, so I know that that sentence is kind of blasphemous because degrees is the only way that we've seen to measure angles for most of us, but it is fairly arbitrary. Again, how many degrees in that? Right? In the right angle, 90? Is that a natural number to you? 90 degrees? 90 degrees should be something nice. So 90 seems arbitrary to me. Why not 100? I mean, at least 100 would be better than 90. You know, and then the idea that there's 360 going around, I don't know. I've read different reasons for why there's 360 degrees in one revolution. Certainly 360 is not the nicest number we could have picked if we just decided to pick something. But 360 is very close to what natural thing? 365, which is the number of days in a year. So you could imagine yourself, you know, 2,000 years ago, 5,000 years ago, living in some ancient society where they don't have calendars, they don't have iPods and iPads to tell them what day it is. There's no months, and we're not counting. And so all you know is that, like, you know, like the position of the stars or the position of the sun or how many hours of daylight you have today, it's probably going to be really close to the number of hours of daylight you had 1 year ago today, right? Like there is some kind of, there's some stuff you can sense without a lot of high-powered tools that might tell you that like 1 unit of time, 1 year has passed. And so if the right number of days is 365 and a little bit, then okay, it's reasonable that they figured 360. And another nice thing about 360, it has a lot of divisors. A lot of numbers go into 360. Not a whole lot of numbers go into 365. I've also heard that because the ancient Babylonians used base 60, that 360 was a very natural number for them to use. What base do we use? We use base 10. When we write down a number like 324, that 3 is not 3. That 3 is 3 10 squareds, right? Okay, well that 3 would not mean 10 squareds. So the Babylonians, the 3 would tell you how many 60 squareds you had. And the 2 would tell you how many 60 to the firsts, and the 4 would tell you how many 60 to the zeros. Not confusing if everything you've known is base 60. So 360 is a nice number if your base is 60. I don't know how much I buy into either of those, but suffice it to say there's nothing saying we have to do 360 degrees or anything with degrees. So let's talk about the definition of a radian. Completely different way to think about measuring an angle. So here's what we're going to do. We're going to draw a little angle here. And I'm going to call this angle theta. You don't need to draw this just yet. And I'm going to ask you guys. So the radius of my circle here is r. Pretend it's not necessarily a unit circle. So it's just some radius. And I would like you guys to compare how long the radius is to how long this arc is, the one that the angle cuts out. Which one is bigger? R is bigger, right? It's just like it would take more string to put on top of R than it would to put on the circle. Okay, what if we were to make the angle go out to here? So now theta is all of this, and then the intercepted arc is going all the way there. Now which one is bigger, the R or the arc? The arc is bigger. So if at some point the radius is bigger and at some other point the arc is bigger, then it feels like there's some magical place in the middle where what happens? Where they're equal. That's what we're after here. So if I were to draw, and I'm just going to kind of eyeball it here, but would you guys buy that perhaps if I were to put a piece of string on there and straighten it out, that maybe it would be something close to the length of that, someplace around that. Okay, so if this is R and the length of the arc is R, then that angle that we're talking about right in there is 1 radian. An angle of measure 1 radian is exactly the angle that makes it so that the radius of the circle is identical to the length of the arc that gets cut out. So then what if I were to make my angle bigger and say, for example, put it out here, and suppose that I tell you that this distance is also R, and I ask you guys to find how many radians are in that angle. A couple of people are saying 2 radians. Do we buy it? Yeah, makes sense because it's twice the, each of the little angles is 1 radian. So if you have 2 R's up on your circle, then you have 2 radians is the measure of the angle. That's it. That's what a radian is. Just this magical thing that cuts out exactly the right arc. Okay, so let's take a look at number 2. We'll go to Kyle. Okay, so Niels was a colleague of mine. He teaches math here in Massachusetts as well. And do you guys remember when we did the log scales day, we put up that Excel thing with the different moments in biological history? And there wasn't, like a lot of stuff happened in the last tiny bit of time relative to how long stuff has been happening. So it's the same guy that created this thing. And so were we best friends in college? We were not best friends in college, but we met when we both worked at the same school. And so we are still friends today. We've got, we want the length of the arc to equal the length of the radius. And when those two things happen, how much is the angle? 1 radian. And if we are in a moment like that, then how much is the angle? 2 radians. So it's just a matter of counting like how many radii do you have going around the circle. So what do you think is the measure of that angle? 3 radians. Fair enough. Okay, so we'll skip ahead a little bit and ignore that for the moment. And we will skip ahead and figure out why do we talk about using radians. Okay, so it says using radians makes some formulas simple while the same formula is more complicated with degrees. We're going to come back to this once we get a formula under our belts. So suppose Suppose. I guess we're kind of jumping ahead, but we can do it here. Suppose that I call the, draw a circle again. Suppose that we call the radius r, and we've got some angle there, theta, and then we're going to call the length of this guy right here s. S is the standard letter to use for the length of an arc. And so I want to know some relationship between those things. Well, what did we say again? If you had 2 radii around the circle, then what was the angle? It was 2 radians. Okay, and if it were 3 radii around the circle, then 3 radians. I'm going to write something down. Tell me if you believe it. We take the length of the arc and divide it by the radius. That's the measure of the angle. So how much is the length of the arc in this picture on the right? So that right there is 2 r's, right? Two r's, and then you divide it by the radius, and that kind of like normalizes things and tells you how many, like a s divided by r just tells you how many r's do you have up there in the top. And so here's our relationship. S over r is equal to theta. And for me, I don't have that equation memorized. I have that version, but either way is okay. For me, it was S equals theta times r. So we'll use that formula on the next page, but at least we can come back to Niels's PowerPoint, and I think we'll see that one there. This one. Okay, so that's an equation that now looks familiar. Theta equals S over r. If we were to try to write the same equation in degree mode, like the equation on the left assumes that theta is in radians. And if theta is in radians, then it's a very simple equation. But if theta is in degrees, then for some reason we have this 360 divided by pi. Why we have that is not clear, but suffice it to say, if I had to choose, I'd rather choose the formula on the left to the formula on the right. And then turns out radians are really important in calculus. And I would say that that's an understatement. I mean, like, you're not going to use the word degree a single time when you take calculus. All of calculus is done in radian mode for a couple of reasons. Here's one. We have not seen, well, we're starting to see curves like this, right? We're starting to draw things that kind of go up and down and repeat. So it turns out that this is the graph of the sine function that we just mentioned. And if you graph the sine function from 0 degrees to 180 degrees, you get that thing right there. And it's got an area, right? I mean, there's just some area that's underneath the curve. And it turns out that finding areas under curves is something that calculus is quite good at. And the area of that is about 114.6 square units. Okay, super. Now suppose we look at the same picture in Radian mode. It's the same picture. Turns out it's not 180 degrees anymore, but why, for some reason, there's a pi sitting out here, but it's the same part of the curve. And the area used to be 114.6. The area is now exactly 2. And again, if I had to choose to deal with 114.6 as an area or 2 as an area, I would choose 2. So lots of nice things happen in calculus when you're in radians. Lots of ugly things happen in calculus when you're in degrees. All right, let's go to number 3. Vance. Okay, let's give this a shot. So I always have to kind of pause as I work my way through this calculation, so bear with me. Trying to figure out how many radians in one complete revolution. Basically what I know is that the question is like how many radii can I fit around the circle if I go all the way around? So, like it looks like I can fit, maybe like there's a third r out there. So like maybe I can fit 3 and then maybe another 3. So it's going to be like something like 6, like maybe 6 all the way around, but it's not exactly 6. So the question is, how much is it exactly? Well, do you guys remember the formula for the circumference of a circle? It's 2 times pi times r, right? So this is a formula we've seen before. Okay. So the question is, how many radii can I fit if I walk all the way around the circle? And a couple of people see that we can fit 2 pi of them. I mean, that's what it says. How far is it if you walk around a circle? It's 2 pi times the radius. So if I start my walk here, how many radii have I gone there? I've gone 1, and then we keep walking, and now we're up to 2. And then we keep walking, and we've got 3, and somewhere down there is a 4th one, and here's a 5th one, and a 6th one doesn't quite get me there. What will get me there is 2 pi of them. And 2 pi is like 6 and a little bit, right? Like 6.3-ish. Okay, so then how many radians are in a complete 360 degrees? It's 2 pi. 2 pi radians equals 360 degrees. If you're rotating all the way around one complete revolution, you are rotating 2 pi radians. Okay, and if we divide both sides by 2, we get the identity that I would encourage you to memorize. We'll go to Sarah for number 4. Say the left-hand side again for us. Yeah, just the. It doesn't say 2 on your paper, does it? Pi radians. Thank you. Okay, so pi radians is 180 degrees. This is something worth memorizing. Pi radians is 180 degrees. Okay, let's try number 5, and we'll go to Richard. Okay, so we've got some nice angles here and then some not so nice angles here, and we want to get into radians. And so the way to do it is to multiply by the right thing. Have we mentioned the word foo-foo in this class? Not in this class. In 107, maybe you heard the word foo-foo spelled this way. Anybody remember what it stands for? Fancy form of 1. That is what a foo-foo is, a fancy form of 1. So what we're going to do is we're going to take 60 degrees and we're going to multiply it by a fancy form of 1. Because if I multiply it by anything other than 1, it changes. All right, Stephen, not a fan of the foo-foo? Is this new foo-foo? So here's our fancy form of 1. If you divide both sides of this equation by pi radians, then you get 1 equals 180 degrees divided by pi radians. You buy it? Just divide both sides by pi radians. So 180 degrees divided by pi radians is 1, because they're equal. So don't write this down, but if I wanted to, I could multiply by 180 degrees divided by pi radians. Because what is the value of that purple fraction? It's 1. So I haven't done anything illegal. I was hoping to go from degrees to radians. What will the units be when I multiply here? Degrees squared per radian. That's not what I wanted. So instead of multiplying by that fraction, what fraction should I multiply by? Yeah, we just want to flip it over. Another fancy form of 1. 1 is equal to pi radians divided by 180 degrees. So that's what we're going to multiply by. Anytime we want to convert from degrees to radians, multiply by pi radians over 180 degrees. And so this gives me, let's see, I've got 60, I've got pi, I've got 180 on the bottom. What happens to the degrees? Cancel, that's what I wanted. And what is the unit still here? Now it's in radians. That's what I want. And then you should reduce it. How many times does 60 go into 180? Yeah, so this is a 1/3 pi or a pi over 3. Questions on that one? You actually don't have to write down rad. If you write nothing, it's assumed you are talking about radians. So I'm going to write it a bunch today and then hardly ever again. Okay, can you guys try with your neighbors, B, C, and D? Again, the important thing is to multiply by the fancy form of 1 that's in purple. Okay, so we'll just have a look. Did we get 3 pi over 2 for the second one there? 3 pi over 2 radians. And then the third one, I got pi over 9. Is that all right? Okay, and then the fourth one, pi degrees. Well, what do? Well, I mean, you just multiply by pi over 180. That's always what we do. And if you multiply by that pi over 180, you just get pi squared over 180. That's it. Pi squared over 180. So it's okay if things don't cancel nicely. A lot of our like well-behaved angles, you'll have cancellation, but pi degrees, it's just some angle, and pi squared over 180 is the radian version. Questions on that? Okay, next page, and we'll go to Kate for number 6. All right, so if we have radians and we want to get degrees, we just need to multiply by the right foo-foo. So last time we multiplied by pi over 180, 180 over pi. So multiply the whole thing by 180 over pi, cancel, and write down what you get, and check with your neighbors. So I've got what I hope are the answers here. So 45 degrees is pi over 4. Pi over 4 is still 45 degrees, so we changed it to 2 pi over 3, which turned out to be 120. Is that right? Okay, and then pi over 12 is 15 degrees. And then you notice that they all had pi in them, and having pi in them makes it so that it actually came from some nice angle. Well, it's okay for a radian angle to not have a pi in it, and you just multiply by 180 over pi. So 4 times 180 over pi is 720 over pi. And if you want to type it in, it's about 229 degrees. Any questions on that? So let me tell you, when I was in your shoes and I was taking pre-calculus, I had this in my head. I knew that pi was equal to 180. I didn't have a sense of what a radian was or which one was degrees. I just knew that pi was 180. It was just this wishy-washy, like hazy sentence that I had memorized. And then I would, anytime I had to convert, I would say, okay, I don't put pi. What do I put? I put 180. I just put it. And then 4 goes into 180 45 times. And so I think that maybe some people are doing that kind of thing, and that will get you the right answer, provided there is a pi to start with. But if there's not a pi to start with, well, I was really in trouble when I was in pre-calculus because I didn't know what to do with 4 radians because I didn't have a pi to just replace with 180. So hopefully you guys have a better handle on this than I did. 180 over pi, multiply by that thing. You'll get it right. It doesn't matter what it started with, okay? All right, so let's go on to number 7, and I think we're to Tacidae. Okay, so we've got the whole circle. So how many degrees is in the whole circle? 360, and we're cutting it into 24 pieces. And what do we get when we divide? We get 15. And instead, if we were to think about the whole revolution in radians, how many radians in one revolution? That's 2 pi. Remember, pi is 180 degrees, so pi is only half of the circle. And then you keep going around, and you divide that by 24, and you get pi over 12. All right, so we're going to fill in some more stuff on the unit circle based on these new angles that we have. We can, all the degree things that you put on the unit circle the other day, we're going to put radian, like the corresponding radian measures of them. But it's really, really easy to kind of lose sight of some patterns. So let me show you, you don't need to go here just yet, but here's the first page of the packet. And just take a look. It's kind of fuzzy on my screen, but I think yours is clearer. But like the first angle here is pi over 6, then pi over 4, then pi over 3, then pi over 2, then 2 pi over 3. And being somebody who looks for patterns, I don't like that very much. Like it's not really clear what's happening here, right? I mean, it's just they're like crazy denominators that seem to have like not a whole lot to do with each other. But there is one massive pattern that underlies this whole thing going all the way around. And again, my friend Niels found this, or at least pointed it out to me, and I like it quite a bit. So let's have a look at what he did. This is another PowerPoint. And if we, so here are the same numbers that we saw before, pi over 6, pi over 4, pi over 3, pi over 2, all of those. He said that you're losing the pattern because you're skipping some angles. The first angle that I go to is normally 30 degrees and then 45, but you know, then you're going up 30 and then 15. He says just go up 15 every time. So the first angle really should be 15 degrees, and then another 15 is 30, and then another 15, 45, another 15, 60, another 15, 75. That's one that we skip. Another 15, 90. And if you just keep going 15, you'll get a few that nobody cares about, like 15 and 75. But you'll get all the ones that we care about. And the nice thing is that if you go up by pi over 12s, then you get the patterns that you kind of missed before. And so here's the pattern going around the circle in red. Every jump is just pi over 12. So you can see all we're doing is counting pi over 12s, right? So I don't know if I can write on a PowerPoint. Apparently I can. If you take 2 pi over 12 and reduce it, what do you get? You get pi over 6. Aha! That was the first one in that crazy list of patternless numbers that I found. If you reduce 3 pi over 12, what do you get? You get pi over 4. Pi over 6 and pi over 4. There was no pattern because they were reduced. But if you go back to what they came from, then the pattern is clear. If you reduce 4 pi over 12, pi over 3. Okay, now I see. So what's that? So you can see there's a pattern under here. If you just go by pi over 12s, you can get everything you want on the circle. Just that some of the things are going to be stuff that nobody cares about, like 1 pi over 12 and 5 pi over 12. But the pattern is pi over 12s, then they get reduced, and then the pattern is lost. Okay, so let's go back. That's just kind of highlighting the ones that we care about and then the ones that we don't. All right, so we can go back here. Number 8. 8 will go to Emily. Okay, so go back a few pages. There it is on page 14. And so on page 14, again, we're just going to fill in a few and then you'll do the rest later. But I'm going to do by pi over 12s and then reduce. So the first angle is pi over 12, which I will write temporarily is here. Don't put that in. That's one that we don't care about, pi over 12. The next angle is 2 pi over 12, but we're going to reduce that. What does 2 pi over 12 reduce to? It's pi over 6. Pi over 6 is going right in this slot right here. Pi over 6. Let's see, so that one was 2 pi over 12, so the next one must be 3 pi over 12, which reduces to, that's pi over 4, that goes in this blank right here. So we've already filled in the degrees. You have a corresponding blank for all the radian versions of things. Can you guys just fill in as many as you're able to in 60 seconds and then do the rest later on? Okay, so we'll go down to number 9. I think we're up to Sam. Okay, so the quadrantal angles are just the compass angles. So if I'm going straight up, how many degrees is it to go straight up? That's 90 degrees, but now we're doing radians. What did you guys come up with for the radian? All right, so up at the top there is pi over 2 radians. And let's see, if that's pi over 2, then what must be this half revolution? That must be pi, right? Because that's half of pi and then double it. And then at the bottom? Yeah, it's 3 pi over 2. And for me, again, there's an underlying pattern here. The pattern is pi over 2s. Just go by pi over 2s. This is 1 pi over 2, 2 pi over 2, 3 pi over 2, and 4 pi over 2. But then we reduce the ones that are easy to reduce. So the left one gives you the pi that you guys had said, and the right one is really 2 pi. But again, reducing kind of muddies the waters. So those are our 4 quadrantal angles, the compass directions. And I just want to pause. So I didn't, like I taught pre-calc a year ago, last spring, and I didn't say this thing a year ago because I didn't know it, but I've since learned that there is a movement of math folks who want to get rid of pi as being this important number for circles. I know. And I'm saying this like what's happening 1 week from today. 1 week from today, March 14th. It's Pi Day. Did we not? We mentioned Pi. We mentioned. Did we not? We didn't mention Pi Day last. Oh, oh, yeah. So I'm as excited as you guys are. Yeah, on March 14th every year is Pi Day, 314, right? 3.14. So on Pi Day, I mean, this is why we have spring break. We call it spring break. It's really Pi Day break. We're just acknowledging. And so on March 14th, eat lots of round things, you know, like pizzas and pies and cobblers and things like that. 3.14 slices of pizza, yeah. Yeah, but so I'm very reluctant to say this, like 1 week away from this important date. I'll say it quietly. So it seems strange to some folks that, okay, so what part of a revolution, what fraction of a revolution is that? A quarter of a revolution. A quarter of a revolution is a half of pi. That rubs some people the wrong way. We'd rather a quarter of a revolution be a quarter of something, right? I mean, like a quarter of a revolution should be a quarter of this magic number. So, okay, I can't change pi. Pi is 3.14 and it always will be and always has been, but I can make a different number that gives me the right fraction thing up here. So here's the different number. Any Greek scholars in the room? What letter is that? It is a T. What is the Greek T? It's not a theta. So this is tau. And some folks would like to say that pi is not the number we should be thinking about for radians. We should be thinking about 2 pi. We should be thinking about tau. And so then, again, what fraction of the revolution did we say that is? It's a quarter. And guess what? This is 1/4 tau. Gets me up there. And what? Well, you know. You're talking about my friends right now. What fraction of a revolution is that? That is half of a revolution. Wouldn't it be wonderful if this was half of something? So it's half of tau. Okay, so I'm just mentioning it. We'll stick with the convention of pi. All right. So we've got these radian, whoopsies. We've got these radian measures up here in terms of pi, and what I'd like to do is maybe ask you, you know, like in which quadrant is 3 radians? This is the angle I'm thinking about. 3 radians. A couple of votes for the second quadrant. How can you tell? Where is 3 radians? That's it, because 3 is slightly less than pi. We didn't quite rotate around to get to the pi line, which is due west. Okay, so then maybe it's important for us to have a sense of what these numbers are as decimals, roughly. Okay, so pi is like, you know, it's about 1.5. Not exactly, but it's close. That was pi over 2. And then pi is around 3. And 3 pi over 2 is around 4.5. And then 2 pi is around 6. So then if I gave you a different angle and I said, okay, I'm thinking of an angle that is like 4.1 radians. Can you guys hold up the number of fingers? That is the quadrant. Where does 4.1 radians live? I see lots of 3s. 3 is a good thing because 4.1 is between 3 radians and 4.5 radians. So 4.1 is down there. So with this very rough estimate, I could just give you any radian measure I want and you can know where it is. And that's something that's kind of nice because if I say, you know, like, what did I say, like 304 degrees, which quadrant is it in? 304 degrees. Hold up the number of fingers. 304 degrees. So it takes a moment. We think about it, and then we say, okay, it's in the 4th quadrant. You have some intuition about 304 degrees, even if you've never thought about that angle. We need to start building that intuition with radians. You've never thought about a 4.1 radian angle before. But if you know that 3 is there and 4.5 is there, then 4.1 is somewhere in between. Okay, so then, so let's go back to our game here with the angle of 3 radians. And I want to know what are the signatures of sine of 3 and cosine of 3. Okay, so first, maybe this is the only time you've ever seen the word signature in a math class. Does anybody know what the word signature means in a math context? If I cover up this part of the word, what does signature mean? You've talked about the sign of a number in a math class, right? Positive or negative. The word signature is the full-on word for what we call the sign. Is the number positive or is the number negative? The reason I'm using the word signature here, well, we want to be real fancy, right? Why am I using signature instead of sign? Yeah, it gets darn confusing because the word sign now sounds like the word sign. And so the sine of 3 and the cosine of 3 are two numbers, and I want to know what the sign of those two numbers are. Okay, I want to know the signature. Are these things positive or negative? Okay, let's think about it. Again, remember, is the sine the x coordinate or the y coordinate? The sine is the y, and the cosine is the x. And we have decided that 3 radians is someplace up here. It's actually quite close to due left. So we'll say 3 radians is there. And you are thinking about the x and the y at that spot right there. And all right, so if we're doing sine of 3, that's the y. Is that a positive y or a negative y? Positive y, because we went up. So the signature of sine of 3 is positive. Cosine of 3 is the x. Is that a positive or negative x at that point? That's a negative. So the signature of cosine 3 is negative. And so what you can do is, if you just care about whether something is positive or negative, there's little ways to think about where things are positive. And so we have defined 3 trig functions: sine, cosine, and then tangent hasn't gotten so much attention recently. And it turns out there's this little mnemonic device you can use to remember where the trig functions are positive. So there's an A, and an S, and a T, and a C. And what this means is that in the first quadrant, all trig functions are positive. Sine, cosine, tangent, they're all positive, because what can you tell me about all the x's and y's in the first quadrant? They're all positive. When you move to the second quadrant, what becomes negative? The x is negative, but what's still positive is the sine, is the y value. So in the second quadrant, the sine is positive, but that's the only one that's positive. Cosine is negative, so is tangent. So these letters are supposed to tell you where things are positive. Anything left out is negative. What's the only positive thing in the third quadrant? It's tangent. What's the only positive thing in the fourth quadrant? Cosine. Okay, so then if you have that in your head, then sine of 3 and cosine of 3, well, it becomes easy. Sine is the only thing that's positive in that second quadrant. So sine is positive, cosine is negative. All right, so how are we supposed to remember this ASTC? Okay, well, I've heard a couple of mnemonic devices. One of them, all students take calculus. Wishful thinking. I think actually roughly 8% of the US population ends up taking calculus in high school or college. So it's an overestimate, but maybe it's a goal. I think so. It's difficult. It's difficult to find good estimates of this kind of thing. But okay, all students take calculus. Okay, yeah. All right, so all students take calculus, as we said. Yeah, good. Okay, and then we will go to, oh, this is perfect. Todd, can you read 11? Go ahead. Okay, so this is what Todd was asking about. Do you need to write radians every time? No, you don't need to write it any time. But if you mean degrees, you better put a little degree symbol up there, because without it, I think you're talking about radians. Okay, this is the picture that we mentioned before, and the magical formula that we're going to use below is S is equal to theta times R. S is the arc length, R is the radius, theta is the angle. And so I suppose that's what I meant over here, S equals theta R. And then there's an important note. We'll go to Steve. Can you jump down to 13? So S equals theta r only works if theta is in radians. All right, so we'll go to 14, Melissa. Okay, so let's think about this one. I'll go ahead and mark up the picture that's up above. So we've got a 150 degree angle. So, okay, that's close enough, 150 degrees. And what's the radius here? It's 10 inches. So I'll say that's 10 inches. And I want to know what length of arc is cut off. So the question is, what letter are we after here? We're after S, right? I want to know what S is. Okay, well, we've got our new and improved formula, so let's use it. S is equal to theta times R. So theta is 150. R is 10. And so how much is S? Okay, there's just a lot of doubters in this room right now. 1,500 inches. Could it be? No. Yeah, it's got to be in radians. And so hopefully you buy that at least that answer is ridiculous for this circle, right? I mean, if the circle is 10 inches for the radius, what's the circumference? Remember, it's 2 pi r. So 2 pi times 10. So that's 20 pi, which is around 60. Okay. So to say that it's 1,500 inches for this part of the circle is ludicrous, right? But it's really easy if you're like, it's easy to miss that that's absurd. And it's also easy to get an answer that doesn't look absurd if you're not paying attention. So we don't get to use that formula unless theta is in radians. So let's put theta in radians. So instead of 150 degrees, what do we need to do to fix it to make it radians? Yeah, and then we'll multiply by our correcting factor, pi over 180. Okay, and so we can crunch the fractions together. What do we get there? That's 5, 6, 56, 25 thirds, I think. And if somebody could type it in either in the first form or in the reduced form, then we'll get a decimal. Something around 28. How much? 26? Okay. Is 26 inches reasonable given the circumference is 60? Okay, that's a reasonable answer. Now the fact is, you might have answered questions like this when you took a geometry class in high school. Like you've seen these kinds of questions before, I think. But you didn't use radians because you hadn't seen it before. But you know, you would play this game with proportions, wouldn't you? You'd say 150 degrees is to what's a complete revolution? 360. As the arc that I'm interested in is to what's a complete arc? Was 2 pi r, which we said was 20 pi, right? Like this is what you could do. And then you could solve for S. And you'll get the same answer. I'm not even saying that's like less work than what we did. I'm just saying that like you've answered stuff like that before. The nice thing is that if you have an angle that's in radians, then I'd much rather do this S equals theta r thing. And like we said before, radians turns out to be quite important in a lot of places. So, so we'll use this formula. Okay, 15, and we're up to Topher. Okay, so let's try this one. So we've got a lake, and clearly the lake is a circle, even if it doesn't say so. And it says we're walking 5 miles, and the radius is 2. What's that? 2.5 radians is what? The angle? Yeah. Okay, so let's see if we can agree with what Garrett is saying. So we know we're going to walk 5 miles around this circle, so we'll just estimate that's 2, that's 4, maybe 5 is someplace around there. And again, our magic formula is this S equals theta r. The theta that we're interested in is what angle did you actually walk around this circle? So what was S in this example? That's 5 miles. And theta, I don't know yet. And then R is 2. So do we agree with Garrett's? You said 2.5 radians. Is that right? Yeah. So that's it. You walked 2.5 radians. S divided by R. 5 divided by 2. But you could also figure out exactly where you are on the circle, because we spent a lot of time thinking about points on the circle. And do you guys remember that, let's move this up, that if you're sitting at a particular point, that normally it's an X and a Y. And what have we replaced that with in terms of theta? Which one is the X? It's cosine of theta and sine of theta. Now that assumes you're in a very special circle. That was the unit circle where the radius is 1. But if the radius is anything else, where do you have to put that R? Stick it right in front. So this is maybe the better thing to know. R cosine theta, R sine theta. Okay, let's fill in the blanks for this trip. How much is R? It's 2. Cosine of. We just figured out the angle is 5/2 or 2.5. R cosine of 2 cosine of 2.5. That's the X coordinate. And the Y coordinate, same thing, but with a sign. Questions on that format there? Yeah, and so now for the first time, maybe, we need to be in Radian mode. So to put it in Radian mode, you hit the button that says mode. And down there, the third option, highlight the word radian and hit enter so it is solid, like on the screen. And if we do 2 cosine of 2.5, we should get the X. And same thing for the sine. That's the Y. So we'll just write that negative 1.6 and about 1.2. Let's see if those answers make sense. This is saying from the center of the lake, we are now 1.6 miles west and 1.2 miles north. Did the signs of those numbers make sense? The X is negative because we went left. Y is positive because we went up. Does it agree with the all students take calculus thing? In the second quadrant, all these giggling, you guys are so immature. So in the second quadrant, only sign is supposed to be positive. So only the Y coordinate is positive, the X is negative. Okay. All right, big group thing starting on the next page. Can you guys go as far as you can and I'll walk around?